All right, it's a great pleasure here to announce the next speaker, Masha Baryakhtar from the University of Washington. And Masha will tell us about multi-messenger signals from dark photons around black holes. Please.
Hi, everyone. Thank you so much to the organizers. Just walking around this morning, it's so beautiful here, and yeah, I know we're going to have a great time. And thanks to Katie for a great introduction for fields around black holes. So I'll focus on a specific case of that, which is dark photons or spin-1 particles around rotating black holes, and tell you about some recent work that we think can be very exciting for the field of multi-messenger physics. So just to have everyone on the same page, we're interested in looking for new ultralight particles using black holes. And the kinds of particles that I'm focusing on there are two types. There's axions, or more generally ultralight scalars, and dark photons. So these are, you can think of them as spin 0 and spin 1 particles. And they'll have, in particle theories, they can have a whole range of masses from sub 10 to the minus 12 eV to an eV, which corresponds to billions of kilometers to microns in wavelength. And the exciting thing about this direction is that you'll be able to connect these gravitational probes of new ultralight fields with particle physics models like the ones I'm showing here. So we can actually do searches that are independent of any kinds of assumptions, as was highlighted in the previous talk for the specific case of black hole superradiance. And we can try to analyze the searches that we're doing in this particle physics parameter space and connect it to other probes of these kinds of physics. So mostly I'll be talking about these dark photon particles, which you can see are also tested in the lab in other stellar environments as well as in the early universe. So the theme of the talk is black holes as laboratories for ultralight particles. And through the process of black hole superradiance, newly formed rotating black hole will spontaneously create a cloud of ultralight bosons in its vicinity if there exists a particle in the theory whose Compton wavelength is of order of the size of the black hole radius. And this cloud will have a density that's comparable to neutron star densities. So these are really very dense clouds that could be made up of these new beyond the standard model particles. So that's, and then we're going to look for signals of these very dense clouds. So that's a lightning summary of the talk. So let's get into a bit more detail. So I'm sure many of you are familiar, but just a quick overview. Superradiance is a process where a wave scattering off a rotating object can increase in amplitude by extracting angular momentum and energy from the black hole. So if you have a wave that passes by which has some angular phase velocity and the black hole is rotating, then through losing angular momentum, it can amplify the wave under certain conditions. Those conditions are given by the superradiance condition, where the phase velocity of the wave, the energy over its angular number, is smaller than the angular velocity of the horizon of the black hole. And this happens for two reasons. One is the black hole is rotating, and the other is the black hole dissipates waves at the horizon. So the relative motion of the horizon, close to the horizon and at infinity, amplifies the wave at long distances. So this is a simulation by Will East that's showing this process for a gravitational wave, which comes in from the bottom in blue, and you can see it will be re-radiated in red just to guide your eye. The outgoing waves are in red, and you can see that the amplitude increases by a huge amount by spinning down the black hole that's at the center there. So initial incoming wave will get re-radiated with much larger amplitude than with what it came in. That said, it's only a factor of a few for gravitational waves and even smaller for scalar or vector waves. So unless you already have a very large amplitude wave, you're not going to get a huge effect. Unless you're able to trap the wave in the vicinity of the black hole, which is what happens if the wave has a small mass, and that's exactly the regime where we're in, where we have new particles that have a mass that creates a potential, just gravitational potential without any further assumptions around the black hole. And then you can localize these waves in bound states and repeat this process continuously so that the superradiant growth becomes exponential. So this turns into a probe of new ultralight particles, which is an inherent instability, classical instability of core black holes. So if these particles exist in the Lagrangian of our universe, a quickly rotating black hole will spin down and populate these modes. So what do these modes look like? For spin 0, basically you can do an analytic solution where you say that you are solving a 1/r potential due to the gravitational field of the black hole. Far away from the black hole, this is quite valid. And so your solutions are characterized by exactly the same solutions as the hydrogen atom, which are also solving the 1/r potential of an electron in a proton's field, except here they're bound by gravity. So your potential is g Newton times mass of the black hole times the mass of the particle over r. And you can get these energy densities that I'm plotting here of scalar fields around the black hole, which are characterized by principal and angular quantum numbers, which give you different distributions of your energy density and different angular momentum. Now, if you match on these solutions that are far away from live mostly far away from the black hole to the ingoing boundary conditions at the horizon, that's what tells you the rate of growth of these states, also known as the superradiance rate. So because there's this absorption at the horizon that introduces non-hermeticity to the problem, and you can get this imaginary piece to the energy, which is another way of saying what I was saying before, you get this exponential growth of the populations of these bound states. And this superradiance rate is added on to the rest energy of the particle, so I'm calling mass of the particles mu, and the binding energy, which depends on the gravitational binding energy characterized by this parameter alpha, which is the ratio of the black hole size to the particle Compton wavelength. And so the superradiance rate can be positive or negative depending on whether the superradiance condition is satisfied. So either the cloud grows exponentially, or if you already set up a cloud somehow through other initial conditions, it would decay for certain if the black hole is not spinning fast enough. Of course, we're more interested in the case where you can spontaneously form these clouds from nothing. So if you go beyond the scalar approximation, we can also analytically solve the spin 1 case, and now it's been done in many different interesting ways. We did it in this matching formalism that I alluded to for the scalar case with May and Robert. So basically, you think of these dark photon clouds, which now have a spin, as slightly more complicated solutions of the hydrogen atom, where now you have total angular momentum as well as orbital angular momentum. So you have this extra vector that can point in some direction. And that makes this matching between the faraway regions and the ingoing boundary conditions a bit more involved, but you get exactly what you expect, which is that you have these spin-weighted angular harmonics solutions to your density profiles. So to compare, for example, for scalar fields and vector fields, you can have different configurations, which in general the profile looks similar, but you can have very large densities close to the black hole for the same total angular momentum for the vector compared to the scalar, because you can have some angular momentum that's just stored in the spin of the particle, and but less angular momentum in the orbital component. So that means that there's less of an angular momentum barrier that pushes the particles further away from the black hole. So that generally means that vector signals and vector rates will be faster because they're more concentrated and sit closer to the black hole. Good. So to give you a sense of how the evolution would happen, let's say we form a black hole. It's observed in a LIGO-Virgo detection event that a new black hole is born with, say, 50 solar masses and 0.9 spin, where here I'm showing the black hole mass on the x-axis and the black hole spin from 0, which is Schwarzschild, to 1, which is extremal Kerr. So if you have a fairly high spinning black hole, these blue regions indicate where this black hole satisfies the superradiance condition. And if it satisfies the superradiance condition at birth, it'll drop down in some amount of time. For the parameters I've picked here, it's about a year. And you can see on the right-hand side, the number of particles in the cloud grows exponentially and reaches a plateau, and the spin takes a drop in the last e-fold of growth. What happens after is that once the number of particles is saturated, which happens when the black hole sits on this line is where that level, the particles in that level have the same angular velocity as the black hole itself, so the superradiance condition is exactly satisfied and the rate of extraction is 0. At that point, the most relevant dynamics is gravitational wave emission. So this very large dense cloud that I showed you at the beginning has a non-trivial quadrupole behavior, and it will emit gravitational waves and dissipate over time due to energy loss. And that's also a very exciting way to look for these particles. So how well can we look for them? Since I'll just say a few words about the gravitational wave signatures, because this is a huge field, and I'm happy to talk more about it if you have questions or during the rest of the workshop. But just to give you a sense of what you can see, for example, let's say you have a merger that you detect in a gravitational wave detector. After you form a black hole, usually after a merger, the black hole has a pretty high angular, pretty high spin, because it captures some of the angular momentum of the binary, even if the two initial black holes were not very quickly rotating. So if you have a quickly rotating black hole, we estimated with our analytic methods that you could see the gravitational waves emitted from a dark photon cloud from a few gigaparsecs away with design sensitivity advanced LIGO detectors. And for scalars or axions, it's going to be hundreds of megaparsecs, because as I mentioned, for vectors, the signals are much stronger. More recent work that actually came out just a few days ago, which is quite nice, by some of my collaborators and who are involved in LIGO and have been doing also really nice numerical GR work to do these calculations very carefully. You can see as a function of the black hole mass on the x-axis and the black hole spin on the y-axis, the reach to these signals can be up to a few gigaparsecs, as shown here. And what they've also done in this paper is try to figure out a much more careful way of doing the data analysis to try to optimize the extraction of the signal from the gravitational wave data if you see it. So overall, it's a kind of a monochromatic signal with an envelope that can evolve in an interesting way. So if you know exactly how to model it, you can get these pretty exciting distances. So even with, potentially the next run of the detectors that's going to turn on now-ish, we might be able to see these signals from dark photons around black hole mergers. And you know exactly, the properties, you know the properties of the black hole mass and spin after it's formed up to the measurement uncertainties, and so you can predict fairly accurately what kinds of signal you can see, so you can use it both as a detection or an exclusion of these types of particles. So that's the end of the gravitational story, and what I want to spend the rest of my time today focusing on is some new work that we finished recently. It was just published last week on connecting these superradiance gravitational wave signals to the particle physics parameter space, and what happens when we consider the simplest kinds of interactions that these particles can have with the standard model. And then it gives you some even the simplest cases give you some very spectacular signatures. So this is what I'm calling mixed superradiance, because the dark photon can have a kinetic mixing. And what we'll see is that superradiance will set up these dark electromagnetic fields, again, at very large densities, which can lead to new electromagnetic along with gravitational wave signatures that can be observed in telescopes. This is the model that we're considering. So you have an action that's a dark photon indicated by the prime fields with mass mu. And then you have a kinetic mixing epsilon between the dark photon field and our photon. So this is a very general model that happens whenever you have any charged particles that at some scale are charged under both gauge groups. And this has been used as a model since the 80s of dark photon interactions. And again, I'm showing here the parameter space. So far we've been talking about the limit where epsilon is 0. So you just focus on the gravitational case. But to really come into contact with what's happening in the standard model and these other probes of these particles, you have to consider what happens at finite epsilon. So what happens if you have non-zero epsilon is that you can think of the dark photon field as giving rise to dark EM fields that can act on standard model particles. So the dark photon field will always be associated with a dark electric field and a dark magnetic field. But in the presence of a non-zero epsilon, those dark electric fields can accelerate charged particles, and the dark magnetic fields can bend charged particles, so our electrons, just with a smaller effective charge. So what happens if you have this black hole superradiance? As I said, you set up this cloud of dark photons around the black hole. For the simplest case, you can just think of an s orbital solution, so no orbital angular momentum, just total angular momentum that's given by the polarization of the vector rotating around the axis of the black hole spin. And if you compute the usual electric and magnetic fields that are derived from this, so the electric field is approximately the time derivative of this vector, and the magnetic field is approximately the spatial curl of this vector, that gives you very large electric fields. So if you take this epsilon parameter at the current experimental bounds from cosmological constraints, the effective electric and magnetic fields are order billions of Gauss. If you can compare that to how much you would accelerate, if you can compute how much you would accelerate a particle across these clouds, since the clouds are also fairly big, they can be hundreds of kilometers in extent, the overall energy that an electron will have at the end as it moves through this cloud, it can be billions, tens of billions of GeV. So these are very large energies and very large boosts. So clearly something exciting should be happening well below these values of these parameters. So what happens? So what we think happens in a scenario is a black hole starts setting up these dark electromagnetic fields. As the cloud is growing, as the black hole is spinning down, you will have some electrons in the black hole neighborhood. The black hole in realistic environments is going to be surrounded by some dilute plasma. There's no true vacuum in our universe. So any electrons or positrons that happen to be around in this dark photon cloud will start to get accelerated. They'll get accelerated to relativistic speeds, but remember that the cloud is rotating, so the direction of the electric field is rotating at a frequency that's approximately given by the mass of the dark photon. So the electrons will bend in these fields, and accelerated bent charges will radiate. The synchrotron radiation that comes out from the electrons will then interact with the background electric field that's already there. Remember, this electric field squared, the amount of energy carried in this electric field squared is as much as the density of neutrons in a neutron star. So these are really, really big electric fields. You multiply that by a small epsilon, but it's still very big. So this means you can have processes like assisted Schwinger, where you can have a photon, energetic photon, in a large electric field background, create an electron-positron pair pretty efficiently. So where does this happen? If you look in this parameter space, the epsilon mass parameter space that I was showing you before, if you zoom in on the region of interest where the Compton wavelengths are of order kilometer scale, these runaway production of charged particles happen basically many orders of magnitude below the current constraints on epsilon. So you can have these effects happen in a large region of open parameter space. So what happens is you start with one electron, and then you get this runaway process where one electron radiates, creates electron-positron pairs, those get accelerated, and then you get this exponential cascade of particle production. And the time scale of this particle production is very fast. So everywhere where it happens, it's fast compared to the superradiance time scale. So that means that as you have the growth of the dark photon cloud due to superradiance, you concurrently start producing this plasma. And so at the end of your process, instead of having a large electric field, what you actually have is some sort of quasi-screened field with a bunch of standard model plasma around that's trying to cancel out the visible part of these dark electric fields. So the question is, what happens? I'm just going to get some water. So what happens once we have these charged plasma and we have these large electric and magnetic fields that are rotating around the black hole that might start sounding kind of familiar to systems that we already have out there, which is a pulsar. A pulsar is a object which has a very large magnetic field that's held up by the neutron star. This magnetic field is rotating around some rotation axis, and there's typically very violent processes that are happening near the neutron star due to these very large electric magnetic fields and generated electric fields, as well as the action of the plasma in its environment. So we were wondering, can we use some of these same techniques to try to understand what's happening with the black hole and dark photon cloud, and can we compute, for example, how much energy is coming out of the system, and can we observe it in telescopes? So I'll outline some differences between the two systems. So one difference is that there's this idea of the light cylinder, which is that these magnetic fields in the case of the pulsar or electric fields in the case of the dark photon cloud are rotating around, and far away from the object, the fields locally are traveling faster than the speed of light. So any charge that's trying to track that electric or magnetic field line can't keep up outside of the light cylinder, which is given by 1 over omega, the rotation speed of the black hole. Is that time or? Oh, okay. Good. So I was confused by the timer, sorry. Okay, so there is, and then you have, then you have magnetic fields that extend out from the neutron star, which is a dipole pattern that is held up by the neutron star matter. So they fall off fairly quickly. So at the light radius, at the light cylinder, there's the magnetic fields are not so large. The opposite case happens for a pulsar, which is that the black hole is rotating fairly quickly, so the light cylinder is pretty close to the black hole, whereas the extent of the cloud, which is the extent of the electromagnetic fields, is given by the superradiance cloud, and it's quite far. So that means that at the light cylinder, there's still quite a large electric field that persists, and you can get a larger signals because of that. Another difference is that if our system is electrically dominated, whereas a pulsar is magnetically dominated, and that's very important because that does not allow us to use kind of the simplest models of modeling pulsar magnetospheres, because the electric field never vanishes, so the dissipation in a system is important. So the charges can never fully cancel the electric field, so you don't never get magnetic field dominance, which is something that's important for pulsars. So let me just skip some of this, the details, because I want to show you the signatures, but I'm happy to talk about it more. If you adapt techniques from simulations of pulsar magnetospheres, which is what Nils, who's a student at Perimeter Institute, was amazingly able to implement. He did this full resistive magnetohydrodynamic simulation in a curved black hole background to track all of the evolution of the electric and magnetic fields to see the energy losses. So here I'll show you a video of the energy dissipation around the black hole. So you can see there's these fun structures that emerge. So this is the rate of energy dissipation around the black hole that's being shown. And you can see there's these clumps and fun turbulent structures that emerge. So we think a lot of the energy dissipation comes from turbulence and from magnetic field reconnection. So these kind of very complex processes that are happening in the environment of the cloud. And the luminosity of these systems, as I was arguing, can be very large because these fields are very dense and extend very far away from the black hole. So here I'm showing the luminosity as a function of this dimensionless alpha parameter that characterizes the system. And the total power, which is dominated by these dissipative losses, can be as high as the luminosity of a supernova, and many of orders of magnitude larger than a typical real neutron star pulsar. So here's 10 to the 38 ergs per second is a total bolometric luminosity of the Crab pulsar, and we're getting up to 10 to the 44 depending on the model parameters. And we think the signal might be periodic. So in the last 2 minutes, I'll tell you about the signatures that we think might be interesting, and I think there are possibly lots of other ideas also, so happy to discuss with anyone who has more thoughts. So basically what happens is you form this cloud, and then you have dissipation both through gravitational waves and through electromagnetic radiation because of these violent processes that are happening around the black hole. So we had two thoughts on searches you could do. Two categories. One is you have electromagnetic follow-ups and black hole mergers. So the same as I was showing before, when you look for gravitational wave searches of a known black hole that just formed. You can do the same with telescopes. So you point at a rapidly rotating black hole that you just discovered in a merger with either an X-ray telescope or a radio telescope. And these plots are showing you the reach with current and next generation telescopes. So you could see some of these events in existing data and potentially orders of magnitude better with future detectors. You could also do the reverse, where you see something that looks like a pulsar, but it looks kind of like a weird pulsar. So you have electromagnetic emission that's periodic, but doesn't quite have standard properties. For example, you have a positive frequency drift, so the pulsar looks like it's spinning up over time. Or you have a bunch of pulsars that happen to have the exact same frequency, because for this black hole pulsar, the frequency is set by the particle physics. It's set by the mass of the new particle. So you expect all of them that are caused by this effect to have the same frequency within a very small spread. So you could follow up these anomalous pulsars, which are shown here. So there's potential candidates with a targeted gravitational wave search, which is being done for regular pulsars, but these particular candidates wouldn't necessarily be chosen to be followed up with gravitational wave searches because they look weird and you might not want to waste your computer time looking at them, but in this case, these would be the targets to go after. So to summarize, dark photons can be looked for with black holes, and these can be directly mapped onto particle physics parameter space with little assumptions about initial conditions. You can look for follow-ups to mergers or anomalous pulsars in a couple orders of parameter space in coupling. and you can have dramatic multi-messenger signals and very exciting plasma dynamics around a black hole. So thanks very much. I'm happy to take questions.
Yeah, thank you very much for this wonderful talk. Are there questions? Yes, we start over there.
Thanks for the talk. Speculative question. So it's about charged black holes. In that case, as I understand, Schwarzschild radius, it should set a boundary condition for these dark photons. And could we expect for something like a Casimir effect in that case? And would it be strong? Because if the cloud of these bosons doesn't produce much of the effect of interaction, maybe we could expect for something indirect?
Sorry, I am not sure I understood the question. You're saying if the black hole is charged, what would the effect be?
Yeah. Then Schwarzschild radius should set a boundary condition for dark photons. And as any boundary condition, it could cause this Casimir effect just because of modification of energy modes,
I mean, definitely, yeah. If the black hole carries some intrinsic charge, it would have quite different dynamics. Black hole, I would not expect it to really carry any standard model charge, just for the reasons that I described before. You don't you always have charged particles flying around, so you will neutralize the charge if it's standard model charge. You could have some dark charge that sources the dark photon, and then you'd have some additional profile, and then you'd have to worry about that. The thing that happens if you do have light charges that are charged under this dark field, you would also start producing those once you get large amplitudes. So yeah, there's lots of extra processes that you'd have to think about.
Okay, thank you.
Yeah.
All right, yeah, we have another question over here.
Thank you very much for the nice talk. So the dark photon black hole pulsar is very, very interesting. So, but compared to the magnetic sphere of pulsars, actually, the magnetic sphere of pulsars is not solved yet after this more than 50 years.
Yes.
And here, your model is different because your electrons are not coherent. And in order to produce enough emission in the radio band, the electrons need to be coherent. I'm not sure. You have showed us emission in the X-ray band and the radio band. What is the emission mechanism for them?
Yeah, that's a great question. So yes, even the pulsar case, which I mean, for some aspects, it's more complicated because neutron stars are messy and there's lots of extra stuff going on. Here you just have a black hole, which is very clean, and this electric field. So what we're able to do right now is we're able to calculate the total luminosity, which I was showing here. We are not able to analyze that, so we're not tracking the actual charged particles, so we can't tell you the exact spectrum that's coming out. In particular, we can estimate what the peak frequency would be, which we expect to be hard X-ray or soft gamma rays, just to calculating the typical emission of electrons in these large magnetic fields. We think there is some overall coherent motion because you do have these very stable background dark electric fields that are rotating coherently, and so there will be some overall direction, coherent motion that you can kind of see here in these coherent oscillations. But I agree with you that that is not necessarily guaranteed. So it's more of a discovery search that we're proposing, that we expect there to be some coherent emission that's happening. We don't know exactly how big it is, but that's kind of degenerate with this particle physics epsilon parameter. So if you see something, you can characterize it and convince yourself it's not a pulsar, but if you don't see anything, it's hard to exclude because you don't exactly know how much power you expect in the radio, in coherent radio.
Thank you. A very quick second question, sorry.
Okay,
so what is the time scale of this pulsar?
So there's two different time scales. So the time scale of the rotation would be tens to thousands of hertz. That's set by typical black hole sizes. The overall envelope of the evolution is set by gravitational wave emission, which can be hours to thousands of years, or even millions of years. Yeah.
All right, further questions? Yeah.
Here's the time scale while someone else is asking a question, if you want to look.
Yeah, thanks for the really interesting talk. I was just wondering, have you looked at like the known pulsar, like because in LIGO Virgo we do like these continuous wave searches for the known pulsars. So is there anything you can say with the results of known pulsar searches to put some constraint on this model that you proposed, just with what we do in O3?
Yeah, so that's, it's kind of related to the answer I was giving previously. So we did do a comparison. So here are some potential pulsars, and these are your existing all-sky searches in dark gray and targeted searches in this line for some particular pulsars, and these are potential candidates. The thing that we don't, here we assume that it's emitting kind of at the maximum value of all of the parameters, and because we don't know exactly how much power goes into the radio band, we just had to make some assumptions about the rate. So for example, here you can see for this pulsar, the strain that you could expect is bounded above, but not bounded below, because it depends on what assumptions you make about how much power goes into the band and which values of epsilon you use. So it's hard to make exclusions. We'd need more simulations, and just, I mean, given that even regular pulsars that we've seen hundreds of, we still don't understand how to solve precisely. I would have a hard time, having a robust exclusion, but I think it's worth doing the searches.
Yeah, thanks a lot.
Yeah, thank you.
Okay, more questions? Yeah.
Okay, so as far as I understand, the dark photons are coupling to normal electrons.
Correct.
So my question is, would you also see effects of the dark photon in like particle collider experiments?
Yes, so sorry, I should have been more clear about this. So the gray region here is existing exclusions from other sources, and in particular here it's a cosmic microwave background from conversion of our photons to dark photons during the CMB era, which would distort the CMB power spectrum. This doesn't assume that the dark photons are the dark matter, and neither does the black holes. There's other exclusions at higher masses, which come from laboratory bounds and production in stars. The cool thing about dark photons is that as you take the limit of zero mass, the dark photon state completely decouples. It's a sterile field that doesn't interact with us at all. So all of the bounds decouple at these light masses. And so that's why these are fairly weak here, and you can make some gains with black holes that kind of match their intrinsic frequency and scale to the dark photon mass. Okay. But yeah, there's a whole range of constraints that's shown here and becomes stronger at higher masses as well.
So maybe I can also follow up. So I also wonder whether you have to modify the standard model of the electroweak sector to motivate or introduce a dark photon.
Well, you have to have this additional dark photon, but it fits well into, it's very easy to add an extra U1 without messing up electroweak symmetry breaking or anything. Okay. If this coupling is huge, then you could mess up grand unification at high scales, but those couplings have long been excluded. Yeah.
Okay, I think we have to break here for the coffee break. So let's thank our speaker again for the great talk.